In this video, we'll be factoring by finding the GCF, which is the greatest common factor. Greatest common factor. So this means we want the biggest factor that they all have in common. So that means the biggest number that we can multiply, we can write each of these terms with as a multiplication problem. So in this case, this one is 3 times x squared plus 3 times x plus 3 times 1. So they each have 3 as a factor. And since this one's being multiplied by 1, this one by x, this one by x squared, there aren't any other constants that I could factor out. There aren't any other numbers that I could factor out. And because this one doesn't have any x, there aren't any x's that I can factor out. So 3 is my greatest common factor. So then, just like I'm undoing using the distributive property, I can take that 3 and put it into a multiplication problem with each of these. Because if I were to multiply each of these terms by 3, then I would get my original expression back. So now let's look at some where it's a little less obvious what the greatest common factor would be, because you don't have the same number in front of each thing. What if I have 3x squared plus 6x plus 18? So just like in the previous example, I know I can't factor an x out of all of these because the 18 doesn't have an x after it. So I'm only going to be able to factor out a number. But which number? And so what I do is I start looking at these numbers and thinking about their factors. And I can tell that all of these are multiples of 3 because I know a multiples of 3 trick. If I didn't, I might just say, well, I know 3 is prime, so if anything can factor out of this one, it's going to be a 3. I'll just get out a calculator and check if either of these are divisible by 3 or if both of these are divisible by 3. So I would have, in this case, 3 times x squared plus 3 times 2x times x, because 3 times 2 is 6. And I might have had to check this on a calculator. I might have had to divide 18 by 3 to see if it was a factor of 3. In this case, I know that it is. That 3 times 6 is 18. And so this time I didn't have to put times 1 because I'm still going to have the 6 there when I'm done factoring. So since I've got each term written as a multiplication problem with a 3, I can factor that 3 on out and put it in front of the parentheses. And then I would have x squared plus 2x plus 6 left over here. So, that doesn't always work because I don't always have a factor I can pull out of each of these. For example, if I have the very similar problem, 3x squared plus 6x plus 17, then there's nothing I can do. I could still write this as 3 times x squared, this is 3 times 2x, but 17 isn't a multiple of 3. I can't factor a 3 out of that because 3 times 5 is 15 and 3 times 6 is 18. So I know 17 isn't a multiple of 3. So I know this doesn't have a greatest common factor. So there's just nothing to do there. I mean, I could factor a 1 out, but that wouldn't change anything. However, if I had something like 3x to the third plus 6x squared plus 17x, then even though I can't do anything with the constants, I could rewrite it as 3x squared times x plus 6x times x plus 17 times x. And then I could factor a variable out because each of these has an x. So I can swoop an x, I can factor an x, but I like saying swoop, out of each of them. And be left with 3x squared plus 6x plus 17. So you need to take a look at both the constants and the variables when factoring. I'll do one more example and then I'll end the video. So I just wanted to show you an example with a little bit more going on. So this one has a couple of things going on that weren't present in the previous examples. The leading coefficient is not the smallest constant, and there's a negative sign. So I start looking at these, and I think, what's the biggest number I can find that I know I can factor out of them? They're all even, so I know I can factor a 2 out, but I might also check for something bigger, and there are a couple different ways I could do that. I could either write factor trees for all of them. I could go ahead and factor the 2 out and then see if there's anything left in my smaller polynomial. In this case, I know 8 has nothing but 2's. It's 2 times 2 times 2. So that means I only need to check if these are divisible by 2, which they are, if they're divisible by 4, and if they're divisible by 8. And I know this isn't divisible by 8 because when I count by 8s, it goes 8 and then 16 and then 24. So I know 20 is not a multiple of 8. So that means I just need to check 4's in addition to 2's. 12 I know I can write as 3 times 4. 8 I know I can write as 2 times 4. And 20 is 5 times 4. So 4 works. And if I didn't see that 4 and divided it all by 2, then I'd get a smaller polynomial that was still even, and I'd realize I could divide it by 2 again. So, you know, I'd have a way to fix my mistake if I didn't see that. So 12 is 4 times 3, x squared, plus 8 is 4 times 2, x, minus 4 times 5. So I've gotten all of these written as a multiplication problem that has 4 as one of the factors. That is my greatest common factor because 3 and 2 and 5 are all prime numbers. So I know they don't have a common factor. So you'll see that I kept that minus sign with the 5 because the 4 I could factor out was a positive 4, so that left that negative sign for the 5. So those are some examples of factoring out a greatest common factor from a polynomial.